selective hydrogenation of 2,4-furaldehyde. And his co-authors are Rongxiao Liu, Dmitry Zemlyanov, Tianpin Wu, Rodrigo Lobo Lapidus, Jim Domestic, and Jeff Miller.
Thank you for the kind introduction. Thank you for the kind introduction. Can everybody hear me? So I said, we're going to be talking this morning about the deactivation of a copper chromite catalyst that we've been using for the selective hydrogenation of furfural, an important intermediate in the biomass to fuels. This work is part of our Institute for Atom Efficient Chemical Transformation, which is a collaboration between Argonne, Brookhaven, Northwestern, Purdue, and Wisconsin, looking at all forms of reactions for the sugars to biomass. For those of you who have followed some of our work, you're probably getting sick of seeing this roadmap, but this is basically our roadmap of sugars to fuels as developed by Jim Domestic. Okay, and we're very interested. We've got projects within IAC working on all of these different types of reactions, and we're studying all those to improve the catalyst and improve the yields of some of these catalysts. Specifically today, what I'm going to be talking about is this reaction here, the reaction of furfural, or furfural alcohol. This reaction right here. Furfural alcohol is an important intermediate on its way to levulinic acid, which can then be converted almost directly to a diesel-like component here by hydrolysis. But what we're trying to do is we're trying to minimize the secondary reaction, in which furfural alcohol can be further hydrogenated to methylfuran, okay, which wastes hydrogen and puts us into a compound that is not as valuable as a biomass intermediate. The catalyst that we're going to be talking about this morning here is a commercial BASF catalyst. It's a mixture of copper oxide on chromia with a metal content you see here, essentially. There's no support other than the chromium oxide for this catalyst. It's been commercialized for a number of years, fairly high surface area for this type of material, but very large copper crystallites. In the argon work that I'm going to be talking about today, we're doing gas phase hydrogenation using this chromia-supported material. We've got a sister project with our collaborators at the University of Wisconsin, in which they're looking at aqueous phase hydrogenation of the same type of copper, but in this case they're using an alumina support. And they'll be, I think that they're reporting on this at the next NAM meeting on what they've been doing with that. This is the a plot of the furfural conversion rate and the selectivities for the various components here. You can see that the selectivity to furfural alcohol is quite high for this reaction at relatively low turnover frequencies here. But most important here is the reaction rate starts out high and drops immediately, and it continues to drop over the course of the 300 minutes on stream that you see here. If we continue this out for several days, it continues to drop over the course of the time that we're looking at. So part of the talk that we're talking about today is we're very interested in the mode of this deactivation and how can we mitigate that deactivation with the various types of chemical treatments. In addition, as we increase the furfural conversion here, you can see that the selectivity to furfural alcohol, our preferred product, goes down. At the same time, the undesired product, which uses up too much hydrogen, going to 2-methylfuran, goes up here. So there's a problem here with overhydrogenation, and we're very interested in seeing if we can cut down on this step as opposed to the step here, which eventually will give us the levulinic acid that we're interested in. Pre-treatment for this catalyst is extremely important. Okay, on the what you would call this, the X sub 1 axis here, We've got a pre-treatment temperature. This is pre-treatment in the presence of hydrogen. And you can see that the best pre-treatment temperature is about 200 degrees C and a reaction temperature of about 200 degrees C. Also, we get the highest furfural reaction rate and the highest yield for this catalyst. If we take it to too high pre-treatment temperature or too high reaction temperature, the reaction goes down extensively. Okay, and we'll be talking about what's going on at these higher temperatures here when we get into the meat of this discussion. Okay, so there's if you look at what we've seen so far, and also look through the open literature, there have been a number of deactivation modes been proposed for this types of catalyst. One is the oxidation of copper for this material. It's believed that by some papers that copper 1 is the active component, and it's oxidized to copper 2 in the reactions. Sintering of copper has also been listed in there. There's a lot of there's some literature that states that chromium is moving over the top of copper and this. And then finally, of course, buildup of carbon on the catalyst has also been implicated as a source. The bulk of the literature states that it's one of these two, that it's an important aspect of this, and we decided to do a more extensive study of what was going on in the catalyst. We tried to pin down exactly what was going on here. First thing we did is look at the XPS of a fresh catalyst shown at the bottom here and a used catalyst shown at the top here, and concentrate on final two columns in this chart on the right, which is a quantitation of what you see over on the left here. The fresh catalyst only has essentially the carbon that comes from the open air of carrying it across the room that is collected here. That's number one. Very little oxygenated carbon showing up on the surface of this catalyst. After the catalyst has been used for a day or so on stream, we do the same experiment here, and what we find is a whole series of oxygenated materials that are absorbed on the catalyst and cannot be easily removed from the surface of the catalyst. These are both alcohol, ether materials, which make up the bulk of this material, but we also see various types of carbonyl and acidic components also appearing on the surface of the same catalyst. Okay, we've also looked at the metals on here using Auger and XPS. Okay, and what you see first is here's the starting material, which is this copper oxide, chromium oxide type material. And what you see in this plot here is two different conditions. The material that's been reduced at 200 degrees, which I said is the most active catalyst, and the material that's been reduced at 300 degrees, in which we get a significant drop-off in the activity and selectivity of this catalyst. If we look at the Auger, which can tell us something about the oxidation state of the catalyst, the initial material, which we received from the manufacturer, is primarily copper 2, okay, with a little bit of copper 1. There's almost no copper 0 from this. When we reduce it at either 200 or 300 degrees, the 200 degrees again being the preferred material, we reduce it completely down to copper 0, and there was almost no copper oxide left for this material. The XPS also tells us a bit on here, and again concentrate on the final column here, which is the ratio of the chromium to copper that we see on the surface of this catalyst here. The initial material has a low ratio of chromium to copper, but as we reduce the material at low temperature first, and then to high temperature, we see an increase in the amount of chromium that's appearing over the top of the copper for this material. Okay, and remember that one of the modes that we were saying is the movement of the chromium over the top of the copper. We see this showing up in the pre-reduced catalyst. We've also looked at the actual fresh and used catalyst here, and you can see that there's definitely an increase in the amount of chromium that is moved from the support over to the top of the catalyst. In addition, notice that when we reduce the material at 300 degrees, we get a significant increase in the amount of chromium that's going over the top of this catalyst. We also been doing some Zane's work. Everything seems to be at argon, an X-ray absorption experiment there. And at the left-hand side here, you can see the reference material. The red here is our starting material in the oxidized form here. And compared to the Zanes of either a copper oxide or a copper foil, you can see that definitely we've got a material that is in the oxidized state rather than the reduced state of the material. On the right-hand side, if you're close enough to the screen, you can probably see that there's actually 3 curves here, okay? Maybe even in the back. So, but basically, when we reduce this sample, everything goes to reduced metal, and this lines up directly on top of the Zanes for the copper foil. So the active component here is a copper 0 component, not copper 1+ that has been pushed heavily by the open literature there. This is just some first derivatives of the Zane spectra. We actually use the first derivatives a lot to analyze these because you can see the changes for that. I'll skip over that for lack of time here. Okay, so the Zanes tells us a lot about the oxidation state. The X-AFS tells us what things are bound to and the size of the particles that we're dealing with. Okay, again, we use the real and imaginary portion of the X-AFS here to gain the information about the size of the particles and what they're bound to. What you can see that is in going from the reduced, from the starting material to the reduced state here, the copper crystallite sizes do not change very much. The fresh crystal has an average copper size of about 5.5 nanometers. Under used conditions, it gets a little bit larger, but it's not significant. We don't feel that this is significant under these types of conditions. In addition, again, pointing back to the Zane's work, all the copper seems to be in the copper 0 state, and there's no evidence for copper 1 or 2 as the active component has been pushed by the open literature. So as I said, the open literature seems to support these. What we believe is, in our current work, that these are the 2 primary methods of deactivation of this catalyst. The movement of chromium from the chromium oxide sublayer to over the top of copper, and then the buildup of these oxygenated carbon materials on the surface of the catalyst. Cartoon-wise, basically this is what we see. We think we're seeing that we start out with copper metal on top of chromium oxide, and some of the chromium oxide creeps over the top of the catalyst, losing the surface area that we have here. In addition, we get these oxygenated spaghettis that are absorbed quite strongly onto the surface of the catalyst, giving rise to a loss in activity over this catalyst. So, the problem with the catalyst then opens up an opportunity. Okay, can we minimize that catalyst deactivation? And one of the techniques I'm going to talk about here is the use of overcoating, which is something we've been developing over the last year or so through IAC. Many of you may be familiar with some of the work that Peter Stair has been doing. He's a member of IAC, working both at Northwestern and at Argonne. Peter, we've been using atomic layer deposition for a number of years in IAC for both making specific metal particles and alloys on here. And one of the things we were very interested in doing, or Peter was interested in doing, is overcoating the material with alumina ALD and finding out when we lost information to the palladium that he was looking at on the source of that. They found out that information, but they did one extra experiment in which they heated this material up to 700 degrees in oxygen, and they found, lo and behold, that they actually got some communication back to the alumina surface because the formation of these cracks which are in the nanometer size scale onto there. And the nice thing about in this specific catalyst, they found that the alumina overlayers specifically goes to the edge and corner sites, preferably to the face sites, giving rise then to dehydrogenation with very little coking for this catalyst. So we've been using ALD overcoating recently to cut down on metal sintering. Okay, we actually build little domes over the catalyst there, and there's no way for the two materials to get together. And sintering has been a common theme throughout this morning's talk. We also are interested in cutting down the deactivation, controlling reactant and product diffusion, and we're also interested in not only just putting alumina here, okay, we're actually putting different layers up on the sides of these catalysts for creating bifunctional catalysts. For example, hydrogenation activity coupled to an acidic component there. So we've actually we started out with our copper chromite catalyst, and we've put 45 layers of alumina over that material, then calcined it at 700 degrees. So what we've got now is an alumina overcoating going over the top of our chromia here, and our copper materials still are open to the site here. And you can see by the black curves here's the furfural conversion as a function of time on stream. And not only is it not deactivating, it's actually activating over the course of the time frame, and it keeps on going out there for several days. This is relatively new data, so we don't have a whole lot of information here. In addition, the selectivity to the furfural alcohol, which we're interested in, is very good here. So we've actually cut down on one of the means of deactivation and actually maybe activated the catalyst. So the question is now, let's look back at some more of the fundamentals as to what's going on in these catalysts and see what we can see here. One of the things we've looked at so far is the CO absorption studies using FTIR. And you can see here, here's the copper chromite catalyst to begin with, reduced at either 200 or 300 degrees. You can see the characteristic peaks here. This is due to the chromium oxide, and here's the absorption of the CO here. Okay, here in the blue and the light green, I guess this is this color, is the ALD coated copper chromite catalyst that has been calcined at 700 degrees. You can see we see the same band showing up here. So basically we have not changed the primary component of this catalyst by doing the overcoating as shown here by the CO absorption studies. At the bottom here is some other materials that's being worked on in the domestic group that I'm not going to have time to talk about, but basically they see some of the same bands as we see, and this is for the copper going on gamma alumina under these conditions here. Here's a stacked plot of the TPR zanes for either the uncoated material or the coated copper chromite material. On the left is the uncoated material, and as I said, this is new data. You can see the date which we collected that information. It was just last month. Okay, what you can see here is here's the zanes data as a function of temperature. Okay, again in flowing hydrogen. Okay, this initial material, as I said, starts out as is copper 1 material. Okay, and we see the onset of reduction at around 270 degrees C. That's that peak right there. Okay, and that's done by about 300 degrees Celsius on this scale here. If we go over to the overcoated material, which is on the right here, notice a couple of things. First of all, we start out with some of the oxide material that is already oxidized. Excuse me, is already reduced here. Okay, that's that pre-edge feature there. Okay, we believe that we've seen cases where the overcoated material using ALD actually is a strong reductant. And we believe that where the overcoated alumina is covering over the copper, okay, it's already reduced that material. But the rest of the material, which is still available for reactions, okay, starts reducing at a much higher temperature, about 300 degrees. And you can see that there's a slow progression to the fully reduced material, indicating to us that there is diffusional limitations in this catalyst, and it's hard to get the hydrogen down to the surface of this catalyst, and that's something we're going to be looking at in the future. In interest of time, I won't talk about the other material, which is Jim Domesic's material, and go on to the conclusions of this talk. Okay, in the case of these furfural copper chromite catalysts, the catalysts by themselves have relatively poor selectivity, and they do deactivate quite quickly. We've done both in situ and ex situ, XAS, XPS, and Auger electron spectroscopy to investigate the mechanism. We find that the mechanism for the deactivation is twofold. Okay, first of all, the catalyst poisoning from the development of alcohol type materials that are absorbed onto the surface of the catalyst. Okay, and also we believe that the movement of the copper over the the chromium over the top of the catalyst is also an important mechanism, especially as we deal with higher reduction temperatures for activating this catalyst at about 300 degrees. The other thing is we found that overcoating the copper chromium catalyst with alumina opens up these pores. We believe right now that the alumina is covering over that chromia, preventing it from attacking the top of the copper here. Okay, we believe that these pores that we've generated right now are probably a little too long, so we're looking at changing the amount of alumina that's going onto those materials, and hopefully by changing some of the processes, we can control where that alumina is going onto the surface there. So. Finally, I'd like to acknowledge some of the people that did a lot of the work here. The bulk of the original work was done by Dongjia Liu, postdoc in my group, who's now working for Johnson Matthey. Her work has been taken over by Hongbo Zhang, who's a current postdoc in our group, and they were aided by a lot of the XAF's work by Tinpin Wu, who's now working at APS at Argonne, and Rodrigo Lobo, who's now at UOP. The XPS and Auger work was done at Purdue by Dmitry Zemlinov, who works with Fabio Rivera, and of course my collaborators Jim Domesic and Jeff Miller. Jim is at Wisconsin and Jeff is at Argonne. And then finally, this work is all being done as part of our Institute for Atom-Efficient Chemical Transformations, which is one of these, the 46 Energy Frontier Research Centers that have been set up by DOE. If you're interested in learning more about some of the work we're doing, we've got a very extensive website that lists all the work. And finally, I'd like to, again, add my congratulations to Bert for a very distinguished career and a well-deserved award. Thank you.
Very nice talk. Are there any questions? Overcoating. Very interesting.
Bert? If covering up the chromia gives you better catalyst, does that mean you need to look at, can you replace chromia with something else?
You've read our mind. We're trying to understand how important the chromia interactions with the copper are. Okay, as I said, this was a commercial catalyst, which was purported to be one of the best in the industry right now. Okay, the problem with the catalyst is it's good for doing batch work. Okay, for furfural. okay? But it really doesn't seem to lend itself very well to the continuous reaction schemes that we're interested in. Okay? And certainly you're not going to, if you're going to be making fuels, you're not going to do a batch reaction for this. So one of the things that we're interested in, as I showed you there, the Zane's work that we're doing is very fresh, okay? It was done just a week ago, okay, from that. But the Zane's is going to tell us a lot about what that interaction is, and tying that in with the computational work that's also being done within IAC, we hope to then optimize what type of support we really need there. Because if nothing else, the toxicity of chromium oxide is something we would like to get away from.
One last question?
Just curious, when you saw the catalyst on alumina, I think you said that was stuff that Jim was doing, do you see the same catalyst deactivation? And if so, is there any way to code that to preserve its activity?
Yes and yes. The work that Jim is doing, they have looked at the copper on alumina, okay, and they're doing that in a slurry bed reactor, okay, for this. They see deactivation also from that. We haven't studied that as extensively as we've studied this catalyst yet, as to the mechanism, okay, but based on what we've been doing already with overlaying, they put the same number of overlayers of alumina on there, okay, and they found that basically they got the same thing. They straight lined the whole thing there. I think that what was happening in their case is they're getting sintering of the metal, okay, and a lot of what the overcoating is doing there is basically building a dome over the top of the metal. So, you know, even if it starts to leave the surface of the alumina, it's got nowhere to go. Okay, so we keep those particles apart. Okay, I'm not sure if ALD overcoating could ever be made commercial. Okay, but I think that it's something that ought to be looked at for some of the problems you've been reporting over the course of today with Fischer-Tropsch catalyst. Sintering seems to be a major problem here, so you ought to take a look at it.
Putting up those kinetic barriers.
Yeah, exactly. So, you know, and as I said, we can control the length of those holes just by the amount of alumina that we put on there. So.
Well, and zeolites basically have a kinetic barrier built in.
We think we consider these in another material that we're making called nanoballs. Okay, basically to be zeolites without a lot of the problems of zeolites. A lot of the internal surface area of zeolites is never used, okay, especially as the crystallite gets larger and all that. Here we're only got a limited amount of pore depth to deal with here, but we do see some size and shape selectivity.
Very exciting, very exciting. Okay, let's thank Chris.
Thank you.